So welcome to Algebra 1 for week 23 at One Day Academy. We're going to work on our lessons as usual, obviously, and we're going to start with our supplement. So start with that. So if you have it, get it out in front of you there. It's week 23 in perfect square trinomials. So as I usually do up here, I'll just write what we're working on. 23 there. Let's see if I can get this thing to move off the screen here. Okay, there we go. So week 23. So before we learned about polynomials where we would have something like x squared plus 5x plus 6. And you break it down, right? With this multiplies to adds to chart here, we would have, oops, it's not very good, MT there. So we have multiplies to, and we have adds to, right? So we'd have multiplies to, and that would be the terms for this first term here. There's a number in front of here that's 1 here, and then there's a number here. I'll just write over here. So we had something like the form ax squared plus bx plus c, right? So a times c here is our multiplies to column, so it's a times c. So here we'd have 6, right? And then our adds to column is just whatever the b term is. So in this case, it's 5. So you think of two numbers that multiply to 6 and simultaneously add to 5. So that would be the numbers 3 and 2, because 3 times 2 is 6, then 3 plus 2 is equal to 5, right? Okay, so then what we can do is break this down. We've done this before. We just break it down in terms of these two numbers here. So we'd write x plus 3 and x plus 2. And then if we multiplied these out, right, so use our FOIL method, we multiply. I use some colors here to show, right? We'd multiply first term by first term, so that'd give us x squared. Do first, or we do FOIL, right? So first, and then O is outside term, so x and 2, so we'd have plus 2x. And then the last part of FOIL is I, right? So inside times inside, so we plus 3x. And then last times last, so 2 times 3, so we plus 6. And then finally, right, if we add all these terms up, if we had 2x and 3x, we get 5x, so we'd have plus 5x plus 6. So we'd end up with the exact same thing that we had here at the beginning up here. All right, you see that's the same. So this week we're doing perfect square trinomials. So the form for this is just a little bit different, but it's pretty easy in some ways because we're not having to think of these two numbers. Our form is just like this: x squared plus 2b. So this is a number here. So there's a number here that we're calling 2b, and then we're multiplying by x, and then whatever that number b is, we're squaring it over here. So just like 2 squared, 3 squared, right? It's going to be there. So then if we want to factor this out to its final form, we just have one step here pretty much. Then we'll just have x plus b, so whatever that b term is, and then we'll have equals to, and then just square it. So we'll just have 2. Here, I'll move the 2 up in the top right corner so you can see its exponent. All right, so then if you have x plus b squared like that, that's just saying x plus b times x plus b. All right, and then you multiply it out, and you get this if you use your FOIL. If you want to pause the video now, you can even do that, and then just verify that you get the same thing there. All right, so that's what we're going to do here. So let's do an example real quick. So if we wrote out, as your paper has, right, we wrote out x squared plus 10x plus 25. If you're looking at it compared to this right here, okay, we see it's x squared and then there's plus 10x. So what's different between these two, right? We can see the top one just has 2b and then we have 10 here, right? So there's 10 here. So what we can say is I would just say, okay, well then 2b must equal 10, right? And then if 2b is 10, then we know that our b, right, is just half of that. So we'd say, oh wait, right, if 2b is equal to 10, then my b is equal to 5. And also we'll notice here, right, our last term is 25. And so then if we calculated down here, our b squared, you'd see that that's 25 there. So you can see how that's just exactly what we have up there. So what we do to write this, right, because our goal is to write this right here in that new form that we showed you right here, right, this thing right here. So we figured out our b was 5. So that's all we need to know. So then we just say x plus 5, and then we just write squared. So that would simply be our answer there. So you can see, right, it's just this piece of work right here. We just had this that was given originally in the top there. 2b is equal to 10, so then b is 5. We can write x plus 5 is 10. So we got that. Now let's look at one more example real quick. So if we have x minus 24x plus 144, we can write something similar here, right? We can say instead of 2b equal, you might be tempted to write is equal to 24, right? But what do we see up here, right? Up here, our b had a plus sign in front of it. So down here, we're just going to make sure we carry that along, right? So whatever number is there, including the negative sign. So then we say 2b is minus 24. And so then we have to conclude that b is half of that, right? Because we divided both sides by 2. I can show that, right? Whatever number is in front of b here, I divide by 2. Or whatever number is in front of b. So if you're solving this in any algebraic form, so b then is equal to, you could say 12, but then it's minus, right? So then in order to write this, we don't even have to go into any depth with this number here. But later in this the first 8 problems, if you take a look real quick, right, you see the first 8 problems they ask are the following perfect square trinomials. So the way to check that, right, is just to calculate what b squared is. So b squared in this case, since b is equal to minus 12, and here, sorry, I apologize for this negative sign there. So let's go back here. Our b is equal to minus 12. So if we do minus 12 times minus 12, we'll get 124. I mean, sorry. I'm going with the 24, right? Use your calculator to double check yourself. And then 144. So we can check that off the list. It matches, right? So that's what you're going to do for those first 8 problems. Now, some of these might seem a little confusing if they have fractions, for example. So let's do an example here that we have a fraction. So I think we worked this one out in class. So this is number 4. So number 4, right? We have x squared plus 7x plus 49 over 4. So you can see what we did earlier still applies. So then we just say, okay, well then the number that's in front of this middle term here, right? This one is just 7. So we say 2b is equal to 7. And then b, right? Instead of being a whole number, instead b is 3.5. Okay, so then b squared, if you have your calculator handy, right, then you can calculate that. And I believe it should be 12.25. Okay, so now in order to say yes or no to this question, you want to see if this right here is the same as well, right? So then what are you going to plug into your calculator to determine this? Well, this symbol right here, so I'll just put it in red. This symbol right here, that's in blue, I'm making it red too, right? What does that mean? It just means 49 divided by 4. So if it means 49 divided by 4, you can go ahead and calculate what that is. And like you said, see this number 4 here, they're just asking for a yes or no. So if this number ends up matching 12.25, then you'll know that then you'll say yes for that situation. Okay, and then the last ones there, 9 through 16, are just asking you to factor each of the square trinomials. So let's go back up here and review. So for this one right here, the first one we did, if we have x squared plus 10x plus 25, and they're telling us that it's a perfect square and just telling us to factor, right? We just found out that 2b was equal to 10, and then we said, okay, then b must be 5. B squared, we didn't even need to know necessarily that b squared was 25, except that it helped us double check that it's a perfect square. Then once we find b, right, we found b, then all we have to do is write x plus whatever that b value is, in this case 5, x plus 5 squared. Okay, and then for this second example, same thing. Our 2b instead, right, we have to include whatever sign we have here. 2b is negative 24, and then so then b must be minus 12. So then we can just write, oh, we didn't finish that part, did we? Let's go reviewed that. Right, what are you gonna write here? Well, if you're following what we did up here, right, then we're just going to use whatever our b value is. So we'd simply write x minus 12, and then we'd square it. So we just write it like that. Okay, so if you want to pause, take a break, and just work some of these out real quick. Make sure you understand them. Otherwise, you can start it back up anytime, and then we'll go on to our lessons. Okay, so we're going to go on to our lessons here. So we have lesson 82 here. It's our first lesson. So lesson 82 is our input-output machine. So 82 here. So we could say simply a function is an input-output machine. Okay, you put something in, you get something out. And that's not very kind of scrunched up, but anyway, you get the just this. It's not always easy to write with this pen here. So then we could say that there are 3 parts to a function. Okay, so there are 3 parts to a function. So we'd say there's an input, then there's an operation. There's something you do with that number. And then after that, then we simply would just have what we call an output, right? And this makes somewhat sense, right? So if we have a machine, a normal machine, right? A calculator, for example, then we put something in, we perform some operation, multiply it, divide it, etc., and then we get something out of it. So in this case, we're going to look for a function. We can even use our calculator to help solve the function here. So the only step then say here, right, is I'm just going to say find x, okay, and replace with what is given for the value. Okay, and this makes sense, a little more sense than just second case. So 3 parts: input, operation, output. So find x in your function and then replace with what is given. So go with that. So now we have our example here. We have f of x here. So f of x, all that means is that our function is related to or is dependent on what our value of x is, or it's a function of x rather. Okay, so then we'd say if we said x squared plus 2x minus 7, then that just means that if we have some value of x here, right, so our value of x is the beginning here, so f of x, if we have some value x, then it will go in the place right here, so x squared and then x right here. So x squared just means putting something to the power of 2, or if you put 2 there, for example, right, then you have 2 to the power of 2, and this next part plus 2 times whatever value of x you had, and then minus 7, and that would give you a result. So now if I said, okay, find f, and typically the way you'd say this, you'd say find f of 4. So if we found f of 4, we'd put our x, replace replace our x with what is given for that value. So say 4 to the 2 plus 2, and then there's always an implied multiplication sign in between these. So if I say 2x, it's always implied that I'm multiplying by that value, then minus 7. So then I can just solve this step by step. So I'd say, well, 4 times 4 is 16 here. And then I have plus, and then 4 times 2, or 2 times 4, is 8, and then minus 7. So then if I add these up on my calculator or in my head, right, so I have 24 for this first set of numbers, 24 minus 7, so I'd have 17. Okay, and then that'd simply be my answer there. Now, let's try one more example here. This is the first half of our lesson here is functions. So now let's work with something that looks a little more complicated here. But if I say f of x plus 2, right, you might be kind of confused because it doesn't look like it's a single value, and it's not. We still aren't going to completely be able to solve this. So if we did that, then for this equation up above here, let me move back here, right? So it says x squared plus 2x minus 7. So instead here, I could have put parentheses around this 4 up here, okay, and around this 4 in the second part here. So now, if I want to do this here, because I'm going to put my x plus 2 here, and for my x, I'll have squared, and then I'll have plus 2 times my x value, so x plus 2, and then I'll have minus 7. So earlier in our supplement, right, we actually stated what this x plus 2 squared. Okay, so here, sorry. So see this part on the bottom here, x plus 2 squared. So that just means that we're doing x plus 2 times itself twice. So if you look up here in our supplement, we double checked our answer here, right? So this x plus b squared, we can write it out as two of these in parentheses. So now let's do that for these just to spell it out a little more clearly. Okay, so we just plugged in x plus 2 for x. So then we would write x plus 2, and we'll write x plus 2, and then we'll write plus 2, and then we can go ahead and multiply this 2 through, right? So we're going to multiply by that term, we're going to multiply by that term. So we'd say 2x, right? Because we don't know the value of x. And then 2 times 2 is 4, so we'd say plus 4, and we'd say minus 7. Okay, so let's go ahead and multiply this part out here, right? So we can use our Boolean, so we'd say x squared, and we have plus 2x plus 2x. We're doing first, then doing our outside terms, so these terms, right? So these two terms, and then we do inside times inside, and then last times last. So this last term here would be 4. We'd have plus 2x plus 4 minus 7. Okay, so now we need to add all of our like terms. So we can only add ones that have the same base and the same exponent. So x squared is going to stay like it is because we don't have another one. And then our x's here, we have plus 2x here, plus 2x here, plus 2x there. So we have plus 6x total. So we have plus 6x total. And then we have a plus 4 here, a plus 4 here, and then a minus 7 there. So that's 8 minus 7, so that's 1. So we have plus 1. And that would complete our problem there. Okay, so that's, I think, all the basics of input-output machines there. There's other examples to peruse over as well. So the second part of this lesson is about domains and ranges. Okay, so I'm going to scroll down here. So domains and ranges here. So change my color here. So if we're going to define a domain, I would just say that it relates to x values. And you could say even of a function. Okay? And then range, right? So normally we think of range as being a span of numbers, right? So domain is a span of numbers as well. So, but a range, we typically, when we're talking in math terms, we say that it would be the y values of a function. So then we're going to think of this in terms of like a graph or something. Okay, so let me draw a graph here. If you remember, right, we always label this part of the graph, we label it as x, the x values. Drew these together. So the x values there, and then just put an arrow on the end here, x values, and then over here we label these the y values. So for this couple examples here, we have example 6 here. So I need a bigger graph here. So I was looking for maybe a bigger graph here. So anyway, just to remind yourself that we can scroll back up to this, but domain are x values of a function, and then range are the y values of a function. So let's make a nice big graph here. And turn our book here. So if you don't have your book open, to 82 already. You can see a couple of examples in here. So I'm going to attempt here to draw example 6 here. So example 6, we have here down the middle, right? We have that's the y-axis, this is the x-axis, so I'll go ahead and label this y, this one x, and then a couple tick marks here, so we know this is negative, so this would be -3 over here, and we have +1, +2, +3 for x, and then same thing for y here. We have 1, 2, 3, 4, for example. Those aren't very evenly spaced there, but we'll get the idea. So -1, -2, -3. Okay, now they graph this thing where you have the endpoint is at -2 for x and 3 for y. Okay, so we had this right here, so that's the endpoint. And then what happens is this line goes down to the center of the graph, and then the endpoint is up here at x is 3 and y is 4. Okay, so up here we see me making this little dot here. Not a great dot there, but anyway, I was trying to make it a circle. And then it connects. And you can see on the left side, I have an open circle that they drew in the book, and then on the right-hand side, it's a closed circle. And then they just call this function f. Okay, that's what we've been using before. So then they just say determine the domain and the range of this function here. So if you remember, right, our domain is everything that's in the x-axis. So let's start by listing the top number and the bottom number for a domain. So start with the bottom number first. We go down to, this is -2, right? So we'd say -2. And then if you remember inequalities, right, we had less than or greater to. That's what's going to go in this blank here, and then there's a blank right here. But we're going to go ahead and write x here, and then we'll write our top value. So our top value for x is 3. And then I'm going to actually get rid of this these underlined things. But this is where inequalities are going to go. Okay, so we'd say that these values don't include -2 because of this open circle here. So we'd say that x, for example, is greater than -2. But then once we get up to 3 here on this very right side, right, our x value could be equal to 3. So we'd say that x is less than or equal to 3. So that's what this line on the bottom here is over here. Okay, so that'd be our domain. Now our range, because domain is just looking at the x values. So if I'm down here at if I'm down here at the center here, if I'm over here, right, I don't care what my y values are at all, right? I'm just looking at my x value. Okay, so now let's go back here and talk about range. So range, the same thing. We're going to list the highest number and the lowest number. So our lowest number here is 0. And then our highest number, right, hopefully you can see that it's 4. So for this one, we'll put the y in the middle, right, because we're talking about range. At the center there, right, and now I made a little circle with the red there, but it was never an open circle. So we'd go ahead and say that 0 is less than or equal to y, and then we'd say that y is less than or equal to 4. Okay, so that's how we would go ahead and state what the domain is here. Now, for an example real quick, where we have to actually state something here, we'll go to example 5 here. So example 5 said that f of x is equal to 3. And it says what is the domain? Okay, so domain, and then it says the range. Okay, so they just gave us this one piece of information here about our domain or about our function. So our function is just f of x is equal to 3. So what you'll notice, right, this is just a 3 here, right? This is just a 3. There's no information about what to do with x if it goes into this over here. So domain, again, relates to x, right? So then the domain, we could just say, we could say it like this. We could say all real numbers. Okay, so all real numbers, because it doesn't matter what value for x you put up in here, right? It's always it's not going to make this invalid. So then if we had range, range is our y. So you might remember a while back we actually would say y is equal to f of x like this at the beginning here. So range is our values, our y values. So if I change x to 10, 20, 30, right, it doesn't change the outcome right here, right? This is going to be 3 regardless. So our range here, we'd go ahead and say that we could say that y is 3 if we wanted to, or you just say, as the book said, they just said range. I think they said range of f equals 3. Okay, that makes sense, right? Because if I change the x value to be anything, whether it's a million, billion, or negative a million or billion, it doesn't change the outcome here. Okay, so I think that covers pretty much everything there. Oh, I did want to talk a little bit about square root of a function here. So we have one here. It's actually practice set f. So we did this one in class. So practice set f here. So f said g of x here. So g of x is just, I don't know, they're trying to make sure that you're not fixated on the fact that we used f of x up here, right? Because I've used f of x up here. You want to make sure that you're not fixated on the fact that we're using a different letter. Okay, so g of x, that just means that it's a function of x. So g as a function of x. And then we'll write square root of 3 minus x, like that. Okay, so if I write that, and they ask for domain and range here. Okay, so let me state a couple things here. Okay, so you're familiar with square roots, I'm sure. But this one is a little funny because you're like, well, then what if, my, let's just write one of that. So if I said my g here is, and I say g of minus 1. Okay, we'll do like we did all of our other functions. We go ahead and plug in minus 1 wherever we see x. So we would write square root of 3, then we have to write minus, but then we have to write minus 1, correct? See that? So then we'd end up having to write square root of 3 plus 1, and then we have to write square root of 4, and then we'd have to write, then it's 2, right? Because the square root of 4 just means what number, when you multiply by itself, equals 4. So we'd say 2. Okay, so now what we should be able to see here, well, and now I'll mention as a fact here, okay? So if you have the square root of 0, you can have 0, right? That makes sense. So if you plug it into your calculator, you'll find that. But if you have a square root of any sort of negative number, then this does not equal a real number, okay? Oops. this does not equal a real number. Okay, so we would say that there's no solution for that. You can try to plug it in your calculator. You're going to get an error if you try to plug that into your calculator. So go ahead and try to do that in your calculator. You'll see that you won't get anything real. Okay, so then we'd say, okay, well, if that's true, then what case are we looking at that this thing right here might be less than 0, for example? So then we might go ahead and say, well, then if 3 minus x is equal to 0, then we could say that x here, so let's solve this like we do any other equation, right? We could say if we want to get rid of x on this side, we'd say plus x, right? And then we have to say plus x on this side. So then when you go ahead and say, I'm going to add these up, and we have 3 is equal to x, or a lot of people would just like to write it like this. And so if 3 is equal to x, we'll write x as 3. Okay, so 3 is the border of what our x value can equal. So if we increased our value of x to, let's just make up an example here. So we said g of 4 here. Right, then we have to plug in 4 here, so we have to do 3 minus 4, right? And then we have square root of minus 1. And that's not a value that we can calculate, right? So in our calculator will find out, so we can cross that off. So now, if we, again, using our example here, our g of 3, then if we did that, right, then we have 3 minus 3, then we have square root of 0, which we can calculate on our calculator to be 0. So that's the very limit of our x. Our x can't be larger, right? So if I show you this right here, right? Our x can't be larger than 3, right? Because we tried 4, but if it's larger than 3, we're not going to get any sort of answer. So then if we're going to go back and state our domain and our range here, domain again is our x values, right? Then we'd say that our x values have to be less than 3, but not only less than, we could say that they could be equal to 3, because that's what happened down here in our value here. We still got a valid answer. Okay, so then, and then our range here. Oh, it didn't actually ask us for the range here. But our range of values can really be anything. So this is all asked for, okay? So this last part here, we're doing range. Range, we could think of it as y is greater than or equal to the value of 0, right? Because that makes sense, because we can't have any square root that is below 0. Okay, so that's it for lesson 82. So if you want to take a short break and then come back to work some of your problems in the practice set. Otherwise, we'll move on to lesson 83 here. Okay, so lesson 83 here, we have coin problems. So 83 here. So this is not anything, not anything mind-blowing here. But if I told you, right, I said a nickel, right, a nickel is 5 cents, right? You know that. Let me use this little symbol here, 5 cents. So then if I had 3 nickels, or I can use n, so 3 nickels, right, then we'd say that that's 15 cents. And then if we had 8 nickels, so 8 nickels, right? Then we would say that what I did over here, right? I did 3 times 5 to figure out that. So then over here, then I just say is 8 times 5 cents, and it's equal to 40 cents. So then value of n nickels, so you could say n nickels. Okay, so you see the only difference here is I didn't put a number here. All right, I'm just gonna say n nickels, and then I just say is n times 5, or I could simply write 5 times n like this. So then for all of my other coin values, so I could say that d dimes is 10d, right? Because if I have 1 dime, then I'll have 10 cents, 2 dimes, I'll have 20 cents, so on and so forth. And then I'd say the value of q quarters is 25 cents times however many quarters I have, right? So if I have 4 quarters, then I have $1. Okay, so the process of solving these problems, so this lesson you can title it if you want to on the top, is just coin problems. So let's just keep this on the top here so we can remember this. There are 2 steps here. Okay, so I'm going to write 2 equations. So I'm going to start with 2 equations. So 2 equations here. The first equation is going to be written. So I'll just say write in terms of number of coins. Okay. And then the second one, I'm going to say write in terms of value. Okay, so how much money you actually have. Okay, so then let's look at our example here. So go to example 1 in your book there. So example 1, if you're reading it there in front of you, it says Jack and Betty have 28 coins that are nickels and dimes. Okay, so if we're thinking about this formula here, so example 1, so it says they have nickels and dimes, and they have 28 coins. So I can just say, well, then if I add those up, right, so I can just say, well, if I have nickels and dimes, I'm just going to write n plus d, and then I'll just write equals 28. Okay, so that's my first equation. So I did my first step here. I'm going to draw a line here to separate our second equation. So now, the second part they say if the value of the coins is $1.95, how many coins of each type do they have? Okay, so now don't let this confuse you too much, right? Because they said $1.95. So $1.95, we would think of it in terms of cents. We would say that it's 195 cents. So we can write that down. I'm going to write it down over here and say, okay, well, whatever the total is, it equals 195 cents. Now, if we only have nickels and dimes, let's think about what we said up here. We said that if we have nickels, then they're each worth 5 cents, right? So then if our nickels are worth 5 cents, then we can say 5 times however many nickels we have, and then we'll have that total, right? So if I have 5 nickels and I multiply that by 5 cents, I'll get 25 cents. So we don't know our number yet, but we'll go ahead and write some of this down. So we'll say, okay, then we know it's 5 nickels. Oh, 5 nickels. And then for our dimes here, so 5 nickels. And then for our dimes, it's just 10 times dimes, right? Because they're just twice as valuable as nickel. Let me just write, oops, that's not my D here, and I'd write 10D. So now we have two equations, and as we say before, we have two equations and we have two unknowns. So how are we going to deal with this? You think for a second. You can even pause the video if you want to and think about it. Okay, but now let's think about it. If we have two equations here, two unknowns, what we can talk about is substitution or elimination. Now, probably the easiest thing is to go ahead and substitute. So over here, I have n plus d equals 28. So I know how many coins I have total, and I know they're just nickels and dimes, and I know how much they add up to, $1.95 or 195. So what I can do is I can isolate one of these terms here. So I'm going to choose to isolate my nickels here. So I'm going to say, okay, well, I'm going to subtract dimes from this side, dimes from that side. Then I'm going to add these up. So then I'll have n. Oh, my dimes are going to cancel because I took them away. Now, then I'm going to have 28 minus d. Now you can see the power of this. I don't need to know how many dimes I have. I just have to represent it with a formula here, and then I can write my new equation like this. So now I have a new equation here that's just in terms of nickels. I could have done it for dimes if I wanted to. Maybe that'd be a good exercise if you want to do that at the end of this. So then I have nickels, and you can see nickels are over here, right? So now let's go ahead and substitute it in. So we write 5, and then I'm going to turn this green so you can see what I'm doing here. So then I'll do 28 minus d, okay? And then I'll change back to red here. So then I write 28 minus d, and then it'd be plus 10d is equal to 195. Okay, now what am I going to do? Well, I have my equation here, what we did before in the supplement in our function problem in our last example, right? We can go ahead and multiply these things across. So remember, there's a multiplication sign here between 5 and whatever's here in parentheses. So if I do 5 times 28, you can do this on your calculator just for your benefit there, but this should be 140. And because I multiplied this by this, then I'm going to multiply it here. So 5 times minus d gives me minus 5d, and then I have plus 10d, and then I have equals 195 still. Okay, now I can add up like terms here. So my d's are alike, my number's not alike. So I can go ahead and write this out one more time. So I have 140. If I add my d's up, I have minus 5d and I have plus 10d. So if I have minus of something, right, it subtracts just like a normal number. So then I'm left with plus 5d is equal to 195. Now if I subtract, oops, I want to get my d's isolated. Okay, right? Make sense? So if I want to subtract my d's on the left side here, I'm going to have to take away all my numbers here. So I'll take away 140 here. I'll take away 140 here. And then if I do that, then on this left side, I'm left with 5. Oops. Scroll up a tiny bit. I'm left with 5 times d is equal to 55. Now, if we remember from solving our other problems, right, once I have my d isolated, in order to get my d by itself, I just divide by whatever number's in front of it. So there's a 5 in front of my d, so I'm going to divide by 5 here, and I'm going to divide by 5 here. So if I do that, 5's cancel here, and I'm left with d. You can use a lowercase d, maybe if it makes it a little bit easier, because this d kind of looks like a 0, right? But if you use a d that's lowercase. But anyway, 55 divided by 5 is going to be 11. So now I know my dimes are equal to 11. And then if I know that's true, then I can go back over here to where my n was, right? So my n is over here, it's 28 minus d. Then just say 28, okay, then 28 minus 11 is my number of nickels. And then I just find that to be n is equal to 17. So that's the short of how we'd solve this here. So if we go back just to review our main points here, right? Our nickels are worth 5 cents, so we can represent that with 5 times n, right? This thing right here, represented with 5n. Our dimes are worth 10 cents, so we can represent it with 10 times the number of dimes we have. Quarters can be represented by 25 times q. And then back over here, we're going to write our two equations, right? Our first one is in terms of number of coins, and then our second is in terms of value, and that's what we did right here. So n plus d is 28, because they said they had 28 coins that were just nickels and dimes. And the last part, we have 5n plus 10d, because 5 times the number of nickels will have some value, and 10 plus the number of dimes will have a value as well. And then we substituted, so we solved right here for n, right here on the left side. So we had n is equal to 28 minus d because we subtracted d from that side. And then we substituted that over on the other side. Solve for d, right? So d was 11. So then we back substituted. Right, so you might call this back substitution. We substitute it back up into here to figure out the number of nickels. Okay, so if you want to pause a little bit to work on an example, you can certainly do that. And then come back for our final lesson 84 for this week. So we have 3 lessons this week. Okay, so lesson 84 here. Back to our blue. So 84, we're going to talk about multiplying radical expressions. So multiplying and by radical, right, I mean crazy expressions, but radicals are square roots. So I'm going to put it in words, then I just say multiply inside by inside, outside by outside. Apologies for the sloppy writing with this pen here, but anyway, so inside by inside. Oh, I forgot a D there. So spelling and drawing. So then, if I was going to make a simple example here, I'd have A times the square root of B, and then I'd have times C and the square root of D. So I'd have a times here in between, or a multiplication symbol. So then if I was going to apply this, inside by inside just refers to the fact that I have this on the outside, or I guess, I don't know, you say inside by inside, but these two terms are in some ways alike, right? They're outside of this expression, so then I can write it as A times C, okay? And a lot of times we'll just write AC, but A times C, and then these other two terms, right? B, square root of B, square root of D, are also like terms. So then we would write AC, and then we write B times D. I can draw it like that. So then we're going to talk about some real numbers here. Let's go ahead and draw this out. So for example 1, if you go to example 1 in your book, you'll see that we have 4 square root of 3, and we'd multiply that by 3 root 2. Okay, so the simplest way to do this is like we did above, right? So we'd go ahead and multiply 4 and 3, so we'd have 12, and then we do root 3, or square root of 3 times the square root of 2, we have the square root of 6. And that would be our answer. That's as simple as it is for that one. Now, we might have to do something different for other ones. So example 2 just has a little bit more complexity here. So if we did example 2, we'd have 4 root 3, or 4 times square root of 3, right? And then we're doing times 6 root 6. So the same rules apply here. And we just go ahead, and I'm going to do this one vertically here instead. So I'm going to write 24 here. Well, actually, just to go back real quick, I can go ahead and do 4 times 6, and then I can write 3 times 6 here. Okay, and then I'm still going to leave this thing up above so we can see it. And then I can write 24 square root of 18. Now, this isn't the wrong answer, this is the right answer, but sometimes we want to simplify our answer here. So what we can simplify over here is this part that's in the square root, because 24, right? 24 is just the number 24. But if we have the square root of 18, then we want to think of a perfect square that can go into it. So if I'm going in reverse order, so on the top there you can see I can always multiply these, but I can basically unmultiply what I've written. So I could write this as 9, or square root of 9 rather, times the square root of 2. Because if I multiply those back together, then I just get square root of 18, right? You can see that. So then if I want to write this another way, we can think of square root of 9, right? Square root of 9 just means that I can find a number, or I can think of a number that when multiplied by itself is equal to 9. And that number is 3. So I'd write 3 here, and then I can write square root of 2. So these are all equivalent statements here on the right side. So square root of 18, I can write as square root of 9, square root of 2, and then square root of 9 simplifies to 3, and then I have 3 times square root of 2. Okay, so then if I'll go one step further here. Now I can rewrite this bottom, or this equation on the left side. I'll write it as 24, and then I'd write it as, oops, okay, so I have this, just maybe a look, I'm going to draw it in green just so you can see the difference here. So then I just write it over here, and I substitute it back in. So I have 3 root 2, and then I do 24 times 3, so 24 times 3, and then I'd multiply it by root 2, which just simplifies to 72 root 2. Oops, root 2. And that would be my answer. So you can see this form right here is a little bit simpler than what I had before, which was just 24 root 18. But one way you can check is that you can get your calculator and you can multiply it all out just to make sure it checks out. Okay, so that's radical expressions, and there's one more section to this lesson, and then I promise we're wrapping up. So these lessons are kind of dense, even though we only have 3. A function here. Okay, so we say for functions. Oops, let me drawing here. So say for functions here, functions here have criteria here. Okay, so if we have a function, then we just say that every input as just one output. Okay, so every input has just one output. So now if we're going to, they have some diagrams to draw here. So I'll just draw these last couple here. So if we have example 6 here, example 6, we'll just talk about this real quick. So we had, they put it out, they had y as an input, a as an input, and then m as an input. Okay, I apologize here, maybe I'll redraw my y here. So they had y here, had a here, and they had m. And then they said we had over here, we have potential outputs here. So then we had p, x, and 5. So p, x, and 5. So they said this y goes to p, a goes to x, and then they said m goes to x. But they also said y goes to 5. So they said the question here, they say does this designate, okay, so designate a function, okay, and the short answer, right, and that's the question, is no, right, because if it did, then every input has just one output. So you can see m right here, right, and you see m right here has two outputs, so it can't designate a function at all. So we'd say no, okay, can't do that. Whereas let's look at another one that's going to be valid here. We can go ahead and think of this other function here, or this other representation where we have a, 4, and 7, and then we have 5 and 11 as outputs. Okay, so I didn't draw that before, but these are inputs. So when we were talking about x before, these are inputs, and then this is outputs on this side right here, right? And there's some operation here in the middle here, right? So there's something happening here in the middle, and then you're getting to this output value. So they said a could go to 5 here, and then 4 also goes to 5, and then 7 goes to 11. Now, they said, does this designate a function? Okay, so they said same thing up here. So they says does, or we'll just say, does it designate a function? And so then you can think about this for a second, maybe if you want to pause the video. But now we're back, right? So A goes to 5, 4 goes to 5, 7 goes to 11. So our rule, if you remember, right? Our rule is just that every input has just one output. So for our example 6 there, oh, sorry, I didn't draw this. This is example 7. But for example 6, we had y goes to p, a goes to x, then m went to x and 5. So that doesn't work because our rule up here was that every input has just one output. Now this makes sense, right? If you got your calculator and you got a different output when you plugged in the same thing, you'd be very worried that your calculator was not working correctly. So the same thing is true here. If we have a function, oops, I drew over the page there. If we had a function that was not reproducible, then we know that something's wrong with our calculator, or something's wrong with the function there. So in the second example, 7, a goes to 5, 4 goes to 5, 7 goes to 11. But each input only goes to one output. Okay, and I think that's all that I want to cover there for lesson 84. So hope that's helpful. And as always, ask questions if you need to on email or Google Classroom, and also in class. So anyway, goodbye and see you soon.